All right, here we are, arc length and surface area. We're going to do example 2, parts A, B, C, then we'll pause and do parts D, E, F. All right, because they do have slightly different setup here. But you'll notice, first of all, that I changed the y equals into f of x and the compound inequality into an interval. So again, we have this, and this time I'm going to go ahead and make the graph resemble the exact question we're doing. We have an interval from 0 to 4, and then just a nice continuous curve, and it doesn't matter, you know, that is a parabola, but, you know, whatever. You can draw your general picture with all kinds of curvature, and it's not going to change the math at all. So here's the deal, though. We're going to take that curve over that interval, and we're going to revolve it, as you see here, around the x-axis. So the x-axis, you will note, is a horizontal line. And so that would be our first bit of discussion here in general. Roman numeral number 2, all right? Surface area. If we take this curve and revolve it around this horizontal line, okay, we're not talking about two curves this time, just that one curve. So when this curve gets revolved around here, the mirror image would hit the board down here somewhere, and we would have this three-dimensional figure that looks maybe something like a vase laying on its side. All right? What's the logic if you revolve a continuous function around a horizontal line in terms of surface area? Well, first of all, I want to remind you horizontal lines are always of the form y equals a number. And in this particular question, here we go again. Hello, my name is x-axis, but my friends call me y equals 0. So just keep in mind that would be the specific equation for the x-axis would be y equals 0. Okay, so let's go ahead and put this over here, y equals 0. All right. Well, here's the general picture that we're thinking about here. We're going to use the surface area, the lateral surface area, by the way, of a cylinder to reason this out. So you notice underneath here, I drew a picture of a cylinder, and you know, a cylinder has a straight edge across, and by the way, this cylinder is laying on its side, but a cylinder, as we've talked, is described by its height and its radius. Well, if you think about it, the picture here, the height of that thing would correspond to that curve, the length of that curve, wouldn't it? And then the radius, see, here's what's a little bit different here, is that the radius of a circular cylinder is the same number all the way across the board, isn't it? It's always the same. But on our picture up here, and you'll notice that I put an orange center line here, just like on our revolved picture, the radius here, so to speak, is changing all the time as we travel across that x-axis. So I hope you see the analogy here. It's like we took this nice straight circular cylinder that's laying on its side and put some curvature into it. Now you can just follow the cookbook that's in the slide if that discussion didn't make any sense, but I hope you see the similarities between the two pictures. So if you think about it, the height here would be the length of that arc. We just talked about how to find the length of an arc, didn't we? And then the radius, instead of being the same number all the way across, is going to be what? The distance between the curve and the axis of revolution as we travel from 0 to 4. So anyway, the lateral surface area for a cylinder with a radius and a height is the geometric formula 2 pi rh. Incidentally, when we talk about surface area, we will use capital S rather than the lowercase s. Remember, lowercase s was just the length of the arc. Now we're going to use capital S to represent surface area. So when we want the surface area of that thing, we're going to go capital S, all right? And you see the expression on the bottom of the slide. So what we're doing, and notice the colors again, radius, green, height, red. Well, wouldn't this be 2 pi? That's just our multiplier out in front of there. Now, as just mentioned a minute ago, the radius here, instead of being the same number all the way across on a nice straight circular cylinder, would be as you travel from 0 to 4. Oh, we're going to travel from 0 to 4? let's integrate this thing from 0 to 4, and wouldn't the radius of this, instead of being like I keep saying, the same number all the way across, wouldn't it be the distance between the curve and the axis of revolution, otherwise known as f of x minus k? That's why that's in that note, in the notes there. So the radius expression in this example, wouldn't it be the distance from the curve, which is that function over there, minus the axis of revolution, which is 0. So for this one, it would be x squared plus 5 minus 0. And again, in an effort to color code that would be the green radius expression, wouldn't it? It's changing all the time as you travel from 0 to 4, unlike being the same number all the way across. So I call that the radius expression. All right, I can already tell that I painted myself in a corner with this big ol' S here. Permission to slide this back over. I should have planned better. Doggone it. All right, I'm a rookie at this, I'm sorry. All right, 2 pi integral from 0 to 4, and then this will be our radius expression again. I didn't rehearse this very well, did I? Oh well, that's all right. So that's our radius expression. And then the height, the h in that formula, right, 2 pi rh. The height would be the length of this. Oh, that'd be the length of that arc there, wouldn't it? That would be the analogy to that. And so this is where we go back and we apply that arc length idea to the function that we're working with. In other words, dun, 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 arc length. Yeah, okay. So to get that arc length, we take the derivative of our function, which in this case is simply 2x, all right? And now we're about to put the arc length expression as a substitute for height here. So, square root, remember that recipe we did earlier when we were doing arc length? The derivative of our function squared, by the way, that would be 4x squared in this case if you want to clean it up. I'll be very, very lenient when it comes to cleaning things up on this. And then dx, and that would be the corresponding h, right? So it's like you got a radius expression and a height expression. So 2 pi rh, there you go. Cleanup not necessary, and we're not going to ask you to go ahead and evaluate this because, to be honest, the evaluation of that integral goes beyond any of the integration techniques that we know how to perform. So that's it. That would be the setup for that one. And that's if you're, okay, and I forgot to do this, but let's put it up here. Let's see, where are we? Alrighty. So, as you notice, 2 pi, which is just part of the formula for surface area of a cylinder, lateral surface area, by the way. We're not adding on the areas of the circles on the ends here. We're talking about the lateral surface of that area, of that thing. And it would be the distance between your function and your axis of revolution would correspond to radius, and arc length would correspond to height. There it is. So really part B and C are very similar. The only thing we're changing here when we transition to those two examples would be what's your axis of revolution. So part B, and I think we can make some modifications on this, so I'm going to leave this up here. Part B says, now let's revolve it around y equals 2. So, how's that change the picture? Isn't that just changing this from y equals 0 up here to y equals 2? So, but it's going to be a very similar looking picture. I know this is lazy, but I did this on purpose so we could kind of see the difference as we move from one to the next. So instead of being down here at y equals 0, the axis of revolution is now up here at y equals 2. So I hope when you looked at that, and by the way, that would bring the mirror image of this up a little bit here, wouldn't it? So, you know, complete accuracy of the picture isn't totally necessary, but it's the same looking object. I hope what you saw there was that that would impact the radius expression. Wouldn't the height, so to speak, the arc length still be the same? So we're going to leave that here. We've got our 2 pi, and here we are. We're back to the template for figuring one of these out. We We got the 2 pi. We already talked about the fact that the height, that arc length, isn't going to be affected by this at all. But wouldn't the radius expression in this case now be the distance from the function down to 2? And so wouldn't this just be the distance between the function and 2? So you change that to a 2. And that would be part B. Yeah, we should clean it up. That would be x squared plus 3. That would become 4x squared. Those are things I would assume you could do. I will be totally fine with you leaving it like that. If you want to simplify it, Kylie, go ahead. And again, we're not going to necessarily go ahead and evaluate the thing. So, all we're looking for here is the setup. And then finally, we'll do part C, and then we'll hit pause and come back and do D, E, F, because they're going to be a little bit different. Y equals 25, axis of revolution. All right. Well, all right, we've seen this before, I believe. What you'll notice this time is that the axis of revolution, and this is going to change the picture around quite a bit, instead of being below the curve, it's above it this time, isn't it? So, some modifications on the picture are necessary. And let's see if I can pull this off. So we've got that curve, and we've got the interval from 0 to 4. Now remember, all of this is dependent upon that function being continuous. I'm not going to be tricky. I won't give you one that has an asymptote or anything like that. So this will be, a very straightforward thought process. But here's the difference. This time, the axis of revolution is above our curve. So it does help to have a rough idea of where the curve is oriented. And so actually, I guess in my general picture, the idea would be that the original side of this so-called cylinder is down here below the curve, and we're bringing it up, all right? And so the mirror image of this is going to hit up here. And there we go with that. Now here's where things change then. I hope you would agree with me that the height of this thing is still the same expression. It's going to still be that arc length. But the radius expression, as we travel from 0 to 4, see the radius, on a nice straight edge, whoops, on this one I should have drawn these down here, boom, 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 boom. Not that it matters on this picture, but the idea would be that the radius would be the curve, the axis of revolution minus the curve. Because again, this time, the axis of revolution is above the curve. So instead of f of x minus k, shouldn't this one be axis of revolution minus the function, the other way around, because of that difference in orientation. So, there you go again. These could be flip-flopped depending upon their relative positions. And this time the axis of revolution was above the curve, so the subtraction should be in the other order, note. So, I think that would be all that. Once again, I'm not asking you to necessarily crunch them out. Abigail, if you want to go ahead and try to crunch that out, go for it. I will tell you that's going to require a much more advanced integration technique than we have available to us. You'll notice on this assignment, it just says, set it up. That's it. Okay? All right.